Okay. Turn on device. Alrighty. Well, it's that time of the semester, we're sort of a month into the semester, and you've probably realized you need to do some laundry. You know, things are getting a little crunchy, and it's and you'll be good for another month, or 6 more weeks, or whatever it is. And so what we want to do is to talk a little bit about how one does laundry, and of course this will relate to circuits, as we'll see in a minute. So, as we all know from visiting, the basement, there's 2 devices: a washing machine, which tends to take about 30 minutes to do its job, at least here in the U.S. I was very surprised the first time I did my laundry in Europe and discovered that washing machines take forever, hours. It's like, whoa, how clean can this get? But here in the U.S., they take about 30 minutes. Apparently, we're not so fussy. And the dryer takes about 60 minutes to dry a full load so it doesn't mold in your drawer. Okay, so there's a reason why we at MIT put off doing laundry. And the reason is, of course, doing one load at a time isn't very smart, because first you stick it in the washing machine, and when it comes out, you stick it in the dryer. And you say, aha, how long does that take? And so what we're computing here is the total amount of time, which we're going to call the latency, it takes to process a particular input. So a particular load of laundry takes 30 minutes plus 60 minutes. So the propagation delay of the washer and the propagation delay of the dryer. Your friends are going to find yourself weird. What is the propagation delay of the dryer? Anyone know? It's a propagation delay. So this is a measure of how long it takes to do the processing. It takes about 90 minutes. Okay, so you say, okay, I've got 800 loads of laundry to do. My mom taught me to sort, so everything's sorted into a complete spectrum of rainbow colors so that you can do each load separately. And you say to yourself, okay, it's going to take me a very long time to do the laundry this way. And in fact, at Harvard, of course, this is how they do it. They carefully do one load, and it's all folded into their drawer, and then they do the next load, so forth and so on. And in fact, if you think about this, that is, if they have n loads of laundry, doing it this way will take about n times 90 minutes. So this is sort of very much the combinational approach to doing laundry. The idea is that you sort of completely process an input, get an output, and then you get to start processing your next input. Of course, we all know this is not how they actually do laundry at Harvard. The butler comes and takes care of it. So this is really more the butler's problem than a Harvard student's problem. But you get the basic idea, right? The combinational approach to processing inputs is very straightforward, but tends to be very time-consuming. Okay, the MIT students are a little smarter. They pipeline the process, and today's lecture is entitled Pipelining, and I hope by the end of the lecture you'll say, aha, I really understand pipelining and why we do it, and in fact can even do some engineering about pipelining. So in terms of laundry, the way pipelining works is that once you've got you free up the washer, in other words, you finish the first phase of processing your input, you can then move on and move it to the second phase of processing. And there's no reason for the first phase, the washer, to sit idle. You might as well stick another load in. And in fact, of course, around here, if you don't, somebody else will. So you want to keep sort of these units busy. So this notion of sort of pipelining the system allows some overlap in the processing of inputs. And in fact, at any given time, sort of in the steady state, for instance, look at step 2 or step 3, you can see we have 2 things going on at once. There's 2 separate inputs that are being processed, an earlier input which has made it all the way to the dryer, and a later input which is now sitting in the washer getting stuff done. So what we have here is a pipeline where we're able to do some amount of processing of inputs in parallel. And then if we think about now the total delay is, well, the performance of our system is gated by the slowest element. in our little pipeline of washer and dryer. In this case, that's the dryer. So we say, okay, well, sort of 90 minutes is how often we can sort of advance the pipeline, move inputs from one stage to the next, or from the output stage, out of the problem altogether. And so we expect to take about n times 60 minutes if we have n loads of laundry. Well, that, remember the first stage was a little. We didn't use both machines because we hadn't done enough processing yet to keep the dryer busy. And so, in fact, you can sort of wonder if at the edges our analysis could be a bit more accurate. But in general, in discussing pipelining, we're interested in sort of the steady state throughput, assuming that we have an infinite supply of inputs. In the steady state, how much processing are we doing? So if we had an infinite supply of laundry, then we would basically be seeing a dry load of clean laundry coming out every 60 minutes, out of the dryer every 60 minutes. And the fact that there's this weird startup transient when the dryer is idle, once back in 1973, becomes less important when you're doing the analysis sort of in the steady state. So everybody happy with that as a scheme? Everybody sort of see what I'm talking about in terms of processing multiple inputs and this notion of sort of progressing through the pipeline? Okay. So we're going to introduce two performance measures, latency and throughput. So the latency is when we follow a particular input, your red load, all the way through and ask how long does it take to work. And we can basically measure the time from when the input became valid to when the output that corresponds to that input becomes valid. In our case, clean and dry laundry. And if you're doing Harvard laundry, it takes you 90 minutes because it goes in the washer for 30 and the dryer for 60. So altogether, we've spent 90 minutes doing that load. Okay. At the MIT laundry, it takes 120 minutes. And the reason is that, unfortunately, because the dryer is the slower of the two elements, we sort of have to, even though we got the washer started right away, it sort of sits there for 30 minutes being idle, waiting for the dryer to finish. And assuming that your friendly dorm mates don't come and dump it on the ground, saying, oh, the washer's done, sorry, I need to get started. What we have to do is we actually have to wait two pipeline stages. And remember, the pipeline is sort of moving forward step by step, two pipeline steps. The pipeline is moving storage step by step every 60 minutes because that's how frequently the dryer is done. So that's the latency. The throughput is a measure of the rate at which inputs or outputs get processed. And it can be either one, and because you can't sort of queue things up indefinitely inside, eventually that rate of processing will be equal. But just to make our analysis concrete, let's just talk about the rate at which laundry loads appear all dried and ready to go. And in the Harvard laundry, they get one clean and dry output every 90 minutes. So their throughput is sort of 1 over 90, right? One load every 90 minutes. The MIT laundry, however, produces a new dryer load every 60 minutes. So here we have a situation where we have latency up here and throughput, and you can see what we're doing is that the two systems, one of which involves a two-stage processing of the inputs, and we get started on the next input even though we haven't finished with the first one, okay, allows us greater throughput. So everybody sort of clear on that? Now, it's not often 100% obvious which one of those is more important. So for example, if you think of your processor that you have sitting open in front of you, many of you, there's a 22, 23 stage pipeline in that processor. It's producing, it executes a new instruction, or it sort of produces a result, every billionth of a second or so, if it's a gigahertz processor. Okay, and you can say to yourself, well, if I'm running a program that has billions and billions and billions of instructions, it's going to run for half an hour, trillions of instructions, then I probably don't care how long any particular instruction is taking. I just care how often do I finish an instruction and move on. How about latency? When is latency important? Is someone thinking of an example where latency would be something you'd be really worried about? Yeah.
Like car airbags.
Car airbags is a great example where, really, you're not processing 1,000 I've run into the bridge events. every second. So you're not really worried about the throughput, but you are worried about the elapsed time for processing a particular input. In the case of laundry, you have a hot date tonight and you really want clean underwear, right? And so you're sort of saying, look, it's great that we get a high throughput, but there's a latency issue. You've got 30 minutes. And so you're trying to sort of get into a situation where you as an engineer have to decide whether you're optimizing for latency or throughput. And what we're going to give you today are the tools for sort of making that trade-off. And for many, many, many applications, number crunching applications, in particular data processing, signal processing, things like that, we're much more interested in the throughput than we are in the latency. So we're going to look for ways to improve the throughput of a system without, and probably at some cost of the latency, as we'll see. So that's where we're going. Yes? Is there always a trade-off? We'll concede that in certain situations we can improve the throughput without increasing the latency, but life is almost never perfect in that way. And when we get to some later circuit examples, you'll see why that is.